Well, hello. Thank you all for coming and taking the time out of your evening at 7 o'clock to come listen to the first talk of our climate change seminar series. I'd like to take a moment to mention how this sort of started. And the impetus originally came from Mr. Rene Romo, who's from Senator Udall's office. And he inquired, is anybody at NMSU doing climate change research, and what kind of work is going on in the region? And this got a few of us professors together, and we ended up basically forming a kind of an ad hoc committee. I mean, I don't really think we know who's who in our committee, but nonetheless, we all got together, and basically we, the small group of professors, then suggested climate change seminar or speaker series, and the first person who supported us was the provost and executive vice president, Dan Howard. And then he was subsequently followed by the dean of the College of ACES, Dr. Rolando Flores, and Dr. Enrico Pontinelli, dean of the College of Arts and Sciences, Dr. William Gould, who's associate research dean for the College of Business, and then finally Dr. Brandon Besselmeyer, who is chief research scientist for the USDA Jornada Experiment Range, also is supporting the series. So without that generous support, we wouldn't be able to have you guys here today. We hope to continue the series. We're going to have an additional talk on the 25th of April by Dr. Greg Garfin. And Dr. Garfin is Associate Professor in Climate, Natural Resources, and Policy at the University of Arizona. So please keep an eye out for an upcoming flyer that we'll be posting around, as well as various emails to come see Dr. Garfin's talk on April 25th here at the same venue at the same time, 7 o'clock. But today, for the kickoff of our seminar series, we're going to have our very own Dr. Dave Dubois, who is our state climatologist for New Mexico. He's the director of the New Mexico Climate Center and associate college professor in Plant and Environmental Sciences Department here at NMSU. Dr. Dubois holds a BA in physics from Rutgers, an MS in physics from NMSU, and a PhD in atmospheric sciences from the University of Nevada, Reno. Dave maintains an active research program in air quality and climate, and he provides climate and climate change information and education to policymakers, the agricultural community, industry, educators, and the public. For example, he's currently conducting studies for the Texas Commission on Environmental Quality to understand interactions with the ozone layer in our area, and for the New Mexico Department of Transportation, where he's providing advice on how to reduce the hazards of dust storms on Interstate 10, which seems to be very appropriate for a day like today. But nonetheless, today, Dave is going to be speaking to us about climate and why are we concerned about a changing climate. So without any further ado, here comes Dave.
It's always good to be a guinea pig in a seminar series, so I'm glad you all came out. I really appreciate the good turnout. How's my sound? Does it sound okay in the back? I need some yays, maybe? Yeah? Okay. Make sure I have the sound here. All right, so we're going to be talking about climate and a changing climate, because that's one of the things that really concerns me. And I want to first I'm not going to talk about the science right off. I want to talk more about what values do I have? Why am I concerned? And why should you be concerned about the climate? So that's what I want to talk about. And first I want to, okay, there we go. Find out where my down button. Okay, so this is kind of where I stand. So why am I, as a person who lives in Las Cruces, concerned about a changing climate? I have kids. I have 2 kids. I worry about their future, their opportunities. For example, I grew up, my parents were school teachers, so we spent our summers going around the country and touring around and looking at national parks. We went up to Alaska. Hey, come on in. And we looked at glaciers, and we went all over the place. And for instance, what will a changing climate do to some of those areas? So some of the areas may have glaciers. For instance, Glacier National Park. That's why it's called Glacier National Park. And I remember hiking up there and seeing what the glaciers look like. And what I've talk to people who've been there last year, there's less glaciers. So that's one thing I'm concerned about. In their future, there's a lot of research on how a changing climate has disrupted social patterns and caused actual disputes to go on. There's all kind of videos, books being written about that, about how warring neighbors, because of their water, they're sharing water, and one guy takes more water, and because it started out as a drought, and causes disruptions and people groups across the world. What is that going to look like? Where's the next warring countries going to be starting from, and how is the U.S. going to be part of that? So that's all the things that I think about. I think about my heritage. I am part Navajo, and my family, who still have some relatives who live on the tribal land in the Four Corners. They don't have electricity. They don't have running water. They don't have the conveniences of just turning a switch and getting a nice cool air when it's hot. They don't have the ability to have. They don't have that. And sometimes they do it by choice, but there are some who they don't have the income to do that. So what are the implications of some of the, and we have people in Las Cruces who are in that same boat. We work with the city, and there are neighborhoods who don't even have swamp coolers. I've got a swamp cooler. I can turn a switch on when I'm hot, but a lot of people don't. What about if it gets warmer? What are they warming? Because that's one of the outputs of changing climate is more heat events. And as a scientist, I also know, I study this, and I know what the future could look like, and very much what is highly probable of what it would look like. So it's my social and moral responsibility to be concerned about this and let people know this is what, according to our best laid out science, this is very likely what it will look like in so many years, and we can look through that later in this talk. So, and the last thing I'll bring up is most of us in this room, even if you're a student, you're likely in the top 0.1% in terms of income in the world. And if you are, up in the scale, you're probably in less than 0.01%. So basically, we are controlling, in a way, what goes on in the rest of the world. We have the resources. For instance, our salary, we could donate that to do something. I'm not saying there's a lot of problems with that, because there's how do we get funds to do that? But in essence, we have the ability to solve things that most people can't do. And just picture that graphic I took from a website that shows, all the people behind us don't have the ability to adapt to climate change. They may be living on a river. They can't move. They may be living on a beach or a wetlands. And there's probably millions of people who are, and they don't have the ability to move. We can go rent a U-Haul and go say, I don't like this place. I'm gonna go up to the mountains and live. No problem. But a lot of people can't do that. So that's why I am concerned about climate change. That's what I wanted to share with you first, before I get into some of the details on why is it such an important thing and why we think it's us. So, all right. I always start off with the first question: has the climate changed in the past? And the answer is yes. Yes, it has changed. So if you go back, there's this thing called proxy records. I mean, we didn't have thermometers going back thousands of years. We only have thermometers going back maybe 200 years at the very most likely 100, 150 years, 120 years. So we have to use things like ice cores, sediments that have piled up over the years, all different things that then we can date them by how many layers, how long does it take a layer to accumulate. And this is one of the examples. I really like this area of research because it's fascinating because you can look at fish. There's a part of the fish. I'm sure Dr. Romer probably knows about that. That's sort of a hard bone in their body that you can sort of use as dating. And yeah, otolith. Yeah. So this is actually this graph was based out of 73 locations around the globe and came up with a reconstruction of temperatures. So yeah, and most of all that time in there is, we call that the Holocene. And it was, yes, it was warm. But look at the far right. As you can see, there's this, it was actually getting cooler. And then all of a sudden, boom, there's a spike right at the end. So I'll show you two more examples of that, because I just love this kind of graph here. And so here's another one. Here's my friend, he came up with it, and a lot of people have problems with it, but it's actually one of the most reconstructed data sets now. There's actually one paper I'll show you in the next slide. It actually had 96 co-authors, and they all came up with the same results. So it's actually a pretty cool graph. So, I mean, look, all the different reconstructive techniques, pretty much the same. It was pretty warm, going back 1,000 years, and then it was cooled off. And then the last 100 years, 200 years, it's just this, boom, increased temperature very quickly. And here's this last one with all this. It's called the Pages 2K project, and it's one of the most active things in climate, paleoclimate right now. Is there's all kind of work being done, and the younger generation has sort of taken us over. And like I said, there's 96 authors that contributed to the paper for this graph here. And basically, those are different climate temperature reconstructions in the last 2,000 years for different continents. So we have enough data now to see. I just grabbed a quote from that. It's sort of in the middle there. It says, the most coherent feature in nearly all of the regional temperature reconstructions is a long-term cooling trend, which ended late in the 19th century. And then there we go. And then we'll take it from there. We'll see what goes on. I'd like to put in not only temperature but precipitation. Here's a really neat data set. My colleagues at the University of Arizona have done a lot of work at the Tree Ring Lab at the University of Arizona, and they've been doing tree cores. They take a core of a whole grove of trees, and they reconstruct the temperature. And they calibrated it based off of rain gauges. And this is one is in El Malpais in New Mexico, northwest New Mexico. And the top graph is the actual 10-year smooth. So it goes back to 8200 and BC 200, and goes to right around 1990 or so. And you can see, and I highlighted a particularly interesting period of our climate history in New Mexico, right around AD 300 to 600. We had a really dry period at that time. So just think about how we would adapt to a climate like that when we would have 200 years of really dry areas. What would our agriculture look like? What would our blank look like if we had a 200-year drought? I mean, we complain about having a 4 or 5 year or an 18-year drought, 19-year drought, because that's sort of about the length that we've been in since 1999 or so, give or take a year or so. And we've had problems with our snowpack, our deliveries to our irrigated agriculture in the Mesilla Valley has gone way down, but that's only a blip compared to what we've actually seen in New Mexico. Okay, so let's go back. That's sort of going into a small area. Let's look out to the bigger picture and see what's going on. I like to kind of focus in on what are the drivers. But first we got to see, okay, here's all the information laid out. So this is the NOAA version of the global temperature anomalies. So anomalies meaning you take the average. So you take the 1900, the 2000 average temperature, and you subtract each individual year from that, and then you plot it over time. So you can go back to 1880 and then go all the way to 2017, and that's what this is. So the far left is the cooler times in our globe. We're over toward your left when the blue, and then the warming is kind of the red over to your right. And you can see we've had a pretty consistent warming trend, increasing temperatures, increasing anomalies, all since 1970s, somewhere around there. And this is pretty consistent if you look at individual areas as well as the global average. So, is the climate changing? Yes. So we're already seeing changes, and I'm kind of cutting to the chase real quick. So we were seeing statewide changes in New Mexico of the last decade, were the warmest of this century. It really follows along with that previous graph. The morning lows have been getting warmer on top of the urban heat island. We do have an urban heat island, but we're also getting warmer on top of it. And but it's not all locations. It's not warming at the same rate everywhere. There's a few areas where it's actually cooling in some places. Very interesting. We're getting a longer growing season. So think about the implications if you have a longer growing season. Who has allergies? Raise your hand if you have allergies. A bunch of us have allergies. And so think about if the pollen season started earlier and earlier in the year, and went longer. That's a concern for a lot of our physicians out there, because they're very concerned because there's triggers for seeing things like asthma triggers and just as a plug for the rest of the talks, we're going to try to get folks from the healthcare or a physician to talk about who's familiar with climate change to actually come and give a talk. So stay tuned, because that's one of our we're trying to get somebody from that sector, so who could really address that issue more than I can. I'm more of I take more of the data to look at what are the indicators. The next bullet there is looking at the freezing level. So you have to actually go higher up in mountains to get freezing. It's a slow march up higher. Think about next time you were up in a mountain. Notice the fauna, the bugs and the trees and things like that, the flowers, and think about the diversity as you go up, and it's actually bringing warmer temperatures higher. And there was actually a really neat paper just published. I saw it just this week, saying that the diversity of the higher elevations is increasing, and it was a global. It was like taking that. It was over several continents. So that's an indicator, as one of hundreds of indicators of a changing climate. And one of the things I work in is dust storms. Aridity. So when we have a lack of water, we have drought, and it's not only affecting human health, but I'll show you some examples of it's actually changing our water. It's actually changing our snowmelt timing. So here's just a map I put together. I like maps, and I just put in together areas that have like climate in New Mexico. We call them climate divisions. And just looking at the trends, and I just looked, and this is graph. This is a map that shows you the trend per decade for summer temperatures, June, July, August. And since 1970, when we started to really see them climb, and we're seeing around the 0.6, 0.7, 0.5, and there's in the southeast a 0.8 degree Fahrenheit change per decade over the warm season. So that we're seeing this temperature trend continue, and we're seeing it still. So I laid out. So we're seeing lots of indicators. I teach a class in this, and we spend almost a month and a half or so just talking about the climate indicators and stuff and what's going on. So, but I want to get we don't want to sit here for another several days in this lecture hall. So I'll cut down to why is the climate changing? So let's go through it one at a time. So I like to read mysteries. I don't read a lot, but when I do, I like to listen or read a mystery. So I'll address this as sort of like a mystery. So we'll have suspects like an Agatha Christie book. So we'll address it like that. So we'll have a suspect we found. There's evidence, and we'll interview them one at a time, and you decide which one is the culprit. So are you responsible? Confess! And we'll treat our physical environment that way. Okay, here's our suspects. Since we don't have very much time, I'm going to limit our suspects. We could have a lot of suspects, but I'm going to limit to the actual number here. So here's a few of them. The first one, the sun. So that's kind of an obvious one. It's like, if the sun changes, we should be able to see a corresponding change in temperature, right? I mean, as soon as the sun comes out, it gets nice and warm. So if there's a change in the sun's output, that should be a slam dunk, because we should be able to see that in the air temperatures and ocean temperatures and mid-troposphere temperatures. So how about that one? So okay, we need some more suspects. Okay, the next one, natural cycles. So what's going on? Is there something going on that behind our backs? So it's something that's internal to the Earth's climate systems, things like El Nino. Right now we're just exiting out of a La Nina. That tends to be dry and warm for southern New Mexico, and that's kind of why one of the reasons why we're getting a lot of dust and high winds and not much precipitation and terrible snowpack right now. So what about things like those? Or what about the orbit? So if you ever taken an astronomy class, you notice the Earth, there's got some prescribed ways the Earth goes around, and so periodic cycles of the Earth's tilt and orbit around the sun that causes ice age, that's got to be the cause, right? So that's our second suspect. And the last one, we'll say, well, we got all these volcanoes. Weathering, erosion, other geologic activity. You listen to the Explorer channel, and they have all these bubbling, lava and all that, all that CO2, methane, all that. So that's got to have a big change, impact on our climate, right? So we'll do those three. So they're very, very good suspects because they all look guilty. They all got that shifty eyes, and it's like, okay, we're going to get you. Okay, so let's get the first one. Let's put the light on this guy. Could it be the sun? Oh, he already has a light. So basically the sun, there's our nice Earth. So the sun shines on the Earth, warms it up. That's the light energy. That's the light that we can see, the visible light. And as it does that, it heats the Earth. And it re-radiates, and it re-radiates as heat. And that is light, too, but at a longer wavelength. That's actually returned out to space. And there's a nice balance. We don't have a runaway climate. So as the energy comes in, energy comes out, and it's balanced. We have a nice system here. So what if the sun slowly changes its intensity? We should be able to see some changes in our temperature, right? Okay. We're really thankful of having satellites up in the space right now. And there's actually very thoughtful physicists and engineers actually came up with this satellite network out there that it's been out there since like 1979. And their whole purpose is to measure the amount of incoming sunlight. They're out there staring at the sun, and they're measuring how many photons hit it in the units of watts per meter squared. And this is out in space. So they're continuously monitoring. And as some of those satellites die, they'll launch another satellite and replace it. And that's what the different colors are. So those are all different satellites that have been launched out there since 1979. And their whole purpose is to measure the changes in energy from the sun. They have other purposes too, but that's one of the big purposes. And this group in Switzerland has actually been putting together and reconstructing a what they call total solar irradiance in watts per meter squared. That's what this graph is. And this is as of last week. You could go and grab that. And it shows you this nice periodic ups and downs. And as you know, if you were to get a ruler and measure the number of years between those bumps, it's about 11 years. And if you have taken any science or astronomy, that should trigger something in your mind. Oh, the 11-year sunspot cycle. Yes, that is the trigger for more solar output. They coincide with the number of sunspots. And as you can see, we've had some in 80, right around 1980, right around 1990, and like 2003, and again right around 2014, 2013, we had our peak in the sunspots. Although looks like there's a slight downtrend in the peaks. So very interesting. So, like I said, we follow 11-year sunspot cycle. Each sunspot is a cool region, but overall the sun shines brighter when we have more spots. And the variations in the sunspots alter the intensity of the sun by a 0.08%. But if you average over the Earth, so the Earth's over here, and you intercept the amount of light that goes into it, it actually changes. If you correct for the Earth's albedo, the color, it results in a change in radiation incident on the Earth of about 0.2 watts per meter squared. And if you look at the numbers here, they're about 1,300. So that's on the order of 0.2 versus 1,300. That's sort of the change, the variation that we see in solar input. So I just had to show this picture. There's a picture of the sun from NASA from yesterday, and there's the size of the Earth right there and the size of Jupiter in relation to the sun. That's something we probably have seen. And there's the diameter of 10 or so. So it's pretty big. But how many sunspots can you see? boy, I don't see any. There may be a couple in there, but I don't see. Yeah, there's probably a few up here. There's one here. Yeah, not very many. And actually, NOAA and then their satellites out there, they actually track these sunspots very intensely because they track what they call space weather. And here's an example of the solar cycle sunspot number progression for the last few years. And we're over here. Here's is as of say 9th of April. We're at another minimum in the sunspot cycle right now. And see, like I said, it peaked around 2014 or so, and then we had another one around 2001 or so. We had a minimum, and so between the two of these peaks are about 11 years. So we actually, and then if you look at the number of sunspots, it's actually decreased from the 2001 or so to the 2014. So we actually had a decrease in intensity of the sun by just a teeny bit. So if we plot the Earth's temperature on the same plot scale, time scale as the output of the sun, we should be able to see a correspondingly same warming trend as this output. But we don't. And for a while it did. We did see a corresponding temperature increase when the sunspot increased, but right around the 70s, the actual output of the sun was starting to go down, but we're still seeing the temperature go up, and it's continuing to go up and up. So in all, and looking at the data, I think the sun has an alibi. We don't see the same trend. We don't see that going up. We don't see them following the same trend as the sunspot cycle and the output. Okay, so he can go because I don't really see the fingerprints on him. So let's look at suspect number 2. So let's look at natural cycles. So you think of we don't see too many teeter-totters anymore. I guess they were kind of dangerous. But it's a really good analog, this mechanical analog of, I really like going to teeter-totters. You kind of bump up and sort of, you have to have momentum, and it's sort of as one goes up, the other one goes down. So it's sort of like, the whole thing is not translating up or down. It's anchored to the ground, and one person goes up and goes down. So that's sort of the analog mechanical system to these internal cycles. So it's an exchange of heat between the ocean and atmosphere. Something heats up, it's got to take the energy from somewhere else, and then if something else cools, it vice versa, back and forth. That's sort of the so we can get something like on the order of like a month's variation up to, say, a cycling of, say, 100 years or more. So that's kind of the, what are we looking for? And so one of the most famous ones is the orbital cycles. If you take a class in this is one of the traditional ways of looking at the record of how the Earth rotates around the sun. We've got is over here on the upper left. We've got this thing called eccentricity, and it varies the ellipse of the orbit around the sun. It squishes and goes circular, squishes on a cycle of about 100,000 years. And if you look at B, so the tilt, we have the Earth is tilted, and the actual tilt changes a little bit between 21.5 and 24.5 degrees in about a cycle of about 41,000 years. And the third one is we call precession. Just like you get a top, you spin a top, and it sort of rotates around that axis. So that's a precession, and that actually has a period of about 23,000 years. So all three of them are going on. So you've got the eccentricity, the tilt, and then this spinning top wobble change in cycles. And so if you look back on the records, you can use this to explain the ice ages, what they call glacials, interglacials. And they're actually, if you do and it's one of the things I try to do when I teach a climate class is do a frequency spectrum. If you look at the oscillations, you do like a Fourier transform or some kind of FFT. You can do the frequencies. This is more technical, and you can actually find these periods: 100,000, 41,000, 23,000 in the data. And so that's why we use this to explain like the really long periods of like the Greenland ice sheets, or like the Antarctic, when you do drilling down, and to explain those. So those are our orbital cycles, and they actually change the amount of energy received on the surface of the Earth. So the problem is, and this is going back to 4000 BC to the present, we were cooling, just like that first graph I showed. We were actually cooling going about a few thousand years ago. But then, so here's the top one's the temperature, and right around 1800s to 1900, boom, we were going up. And here's the CO2, pretty much level until right around the same time, and both of them are going up. But I always caution my students, just because something correlates with it doesn't mean that it's causing it. So, it's a clue, but it's not, you can't prove something that way just because it varies. It's like you could get the number of readers in New York Times will increase over time too, right? But it doesn't mean that the readers of the New York Times cause climate change. So we have to look at a mechanistic cause. And so I consider them an alibi. But if you look at this paper, there's a paper published a few years ago saying the next cycle is an ice age. And and this is a quote from the paper, so based on these natural cycles, our current warming period should end within about 1,500 years. So that's a long time from a human perspective, but on a climate perspective, that's not very long. So, and this is another quote, and so we can be fairly sure that we have, whether we like it or not, delayed the possibility that we will revert from our present interglacial, which means the warm period, to a glacial state, a cold period. So we've delayed it because of what we're doing. And that's the quote from this Nature Geoscience paper. It's published a few years ago. So what about other cycles in the Earth? So if we like to see cycles, because there's some exchange going on. So I like to show this graph that shows you the heat absorbed by the Earth. And this is based off of models and observations from buoys and space-based satellites. I guess all satellites will be space-based most of the time. But so when we're looking at, are there times when there's an exchange of energy between the blue, which is the ocean, and the solid part of the Earth, the cryosphere, land, and ice, which is the green? Early on there were, but if we go past 1970, they're both increasing. So if we expected some kind of oscillation that's causing by something internally, we should be able to see this seesawing back and forth here. But we don't. We see both of them, everything increasing, both systems increasing. So where does that energy come from? It's not coming from the oceans. There's cycling. We can actually look at things like these oceanic cycles. And that's another thing we look at as climatologists. So what are all the different frequencies and exchange of energy between the Pacific, North Pacific, Central Pacific, Atlantic and Pacific energy, and then translating that to momentum, which is winds, at different levels. So what about all these oceanic cycles and cycles out there? And some of them like the AMO, like multi-decadal oscillation, the ENSO, El Nino Southern Oscillation, PDO, Pacific Decadal Oscillation. Those are all, energy is cycled from the ocean to the air and back over time. They don't create or store heat. They're just moving heat around, back and forth. And so examples of that are, we call that in our science, the study of science here in the climate science, internal variability. So these are things that go on in the Earth. It's exchange of energy between different places. We call it internal variability of the climate system. They do influence weather patterns. By all means, they do. That's why we get droughts. That's why we get extended droughts in the places, and it actually varies from place to place. While some places are getting drought, some places are getting flooding. So we're seeing it's not like it's a constant warming in some place. We're actually getting cool in some place, and because of some of these oscillations. And we use these all the time in climate science to look at the key for forecasting, and we call those. And we like to look at, so if this area of the Pacific warms up in relation to this area, what is the response in southern New Mexico? And we've actually developed some crude models based off of the past, but we're seeing that a lot of those don't particularly match anymore. they sort of help out, but it's sort of, we can't really predict the future anymore from some of these past events. So we're seeing something else going on. Okay, so those kind of, these internal cycles don't really fit the pattern because they don't really create heat. We're getting heat from somewhere else, and that's outside of the system. So let's look at our other suspect, is geologic activity. So here's a picture of a volcano. I remember going to Hawaii one year, and it was just so awesome to see the lava pouring out. It's like, oh, look at all that. And we could smell it, the fog, sitting there and getting that, it's like, it's hard to breathe. It's all that's got to, there's volcanoes all over the Pacific that are constantly erupting all the time. And one of my former students works for the USGS. He's a volcanologist. He keeps track of the eruptions and elutions. Flies around, airplane doing this. So there's people tracking these all the time. And there's folks in Indonesia, tracking these all the time. And you see these YouTube videos of boom. Those are going all the time. So that's got to have an impact, right? And you've probably seen a lot of the Discover Channel of like these mud volcanoes, which are really cool. There's stuff going on, bubbling up from the ground where these plates meet, leaking carbon dioxide and methane. That's got to have an impact, right? So I like to say, okay, so let's do let's do like a balancing your checkbook. Let's make things simple. I mean, we're not trying to make things simpler, but we're trying to make simpler, but not simple. But let's get an inventory of all the things that we know, and then compare it to the things that we do know. Things like power plant, all the things that we do as humans to make electricity to run the power in this room, to drive our cars, and to take trips to Florida. And then compare that with natural things. I like to do that. We do this in my class. We try to compare. We get the permits from the power plants. We look through them and add up all the emissions and say, well, how many cars does it take to make the equal the power plant? So, those are very useful things because it sort of gives you a sense of, 10 to the 6th, that's a lot, but is that really a lot? So let's compare volcanic CO2 to like a power plant. And this is one that was, we'll blame San Juan power plant. It's, I don't think anybody from San Juan is here. We can blame them. So if we go back and look at their permit emissions for CO2 back in 2012, they emitted 1.1 times 10 to the 7th metric tons of CO2. And if you look back, go do some research, and go and then look up in Google how many tons of, say, Pinatubo. I remember that. It kind of shows you how old I am. The Pinatubo erupted around 1990 or so, and that was just a picture of it right there. I got off the web, and pretty big volcano. It actually was in the southern hemisphere, and that actually emitted about 4.2 times 10 to the 7th metric tons. Compare the two. Do a ratio. Pinatubo versus San Juan power plant. If you think about it, in physics we just do order of magnitudes. We lop off the 4 and the 1s. It's pretty close. 10 to the 7th, both of them. So one volcano equals 1 year of power plant. And that kind of was like, what? I had to do that calculation several times and then look up a few more journals to verify that. And so in essence, this next graph is kind of a little bit complicated, but we'll show you. We'll kind of break it down. So just look at the bullet on the upper left. So that's how much estimated CO2 is from volcanoes. And this is from American Geophysical Union paper. It ranges between 0.18 and 0.44 gigatons, so 10 to the 9th tons, metric tons per year from volcanoes. It's a range, so we don't know exactly, so it's somewhere around there. That's pretty good for geology. That's a pretty good number, narrow it down to that. And if we do an inventory of all the cars, we know how many people are on the earth, and we know how many cities, and we have an estimate of the number of cars per people in each of the major metropolitans, in each of the continents, in each of the places, and how many cars. And if we look at the anthropogenic source, that's us, anthropogenic, we account for about 35 gigatons per year. And that's back in 2010. That's from all the things that we do, CO2 emitted. And I like to pick on just one thing sometimes. If you just pick out how much from the light-duty vehicles, probably the cars that you probably drive. Probably most of us, unless you drive a bike, then then you're excused. But if you drive a light duty vehicle, four wheels, and probably something smaller than a V8, that emits over the whole globe about 3 gigatons. So just even the cars that we drive are more than the volcanoes, and that's just one year. 3 gigatons for just light vehicle. And that graph it shows you the ratio of the amount of people versus volcano. So if it's greater than 1, that means people will emit more in volcano. And the number is definitely more than 1. It starts off right around 20 in 1900. Year 1900, the ratio of people versus volcanoes was about 20. And it sort of level until about 1940, until after the war. And then we started really making cars. So that we liked that car, 55 Chevys, 57 Chevy. We liked those classic cars, and they came up with all kind of new cars, and more places in the earth had more cars. And that slope was sort of like this, and now it's sort of like that. And that's sort of that. And then we get other places, third world, getting more cars. We got China, people buying cars, and we're at up to about 120, 130 ratio of people versus volcano. So that sort of gives us another sense of at least in terms of volcanoes, we emit way more. By my at least, and this is a paper that was published in 2011, and I think we've at least in the U.S. we actually our emissions for vehicles actually eclipse the amount of emissions from power production. It was actually the line crossed. It was like last year. So by all of our vehicles, we burn more CO2 into the atmosphere than all the power plants in New Mexico. In the U.S. I'm sorry, U.S. So some very interesting things that we started to look into them. It's fascinated. So we can actually look and see the volcanoes actually do have an impact on climate. So if anybody says it doesn't, say no. I remember somebody showing you a graph of when the volcanic eruptions when they did spew out all those ash, it actually cooled the climate. We actually saw dips. And this is sort of just common knowledge for climate scientists is pick out when the earth burped, when they showed these volcanoes, you get a dip. And it usually takes a little while because you got one volcano is a point, and it has to spew out all the volcanic ash, and it has to redistribute through the globe. And what it does, a lot of the action is in this sulfur compounds. And the sulfur compounds actually nucleate. And it started off as molecules, and they actually clump together and nucleate into aerosols. And these are pumped way high in the stratosphere. And the stratosphere has a lot, there's not a lot of exchanges between the troposphere and the stratosphere. This stratosphere is pretty high up. That's like higher than you fly when you take a flight. And once it gets pollution that goes up into the stratosphere, it pretty much stays there for decades and decades and decades. I had a friend who worked at Mauna Loa. He had a laser that he pointed up every night, and he was there. One of his jobs is at night. He was there all night, and he was to track stratospheric aerosols, and on top of the volcano. And he was telling me this. I was there in the middle '90s, and he was still tracking volcanic eruptions. And he wasn't sure where they were coming from, but he was like, "There's a lot of volcanic ash up in the stratosphere." And it was like, it's more of you have to look at trajectories and stuff, but there's a lot up there, and it's from these volcanoes, and they last, more than 10 years. And it's actually, you can see the eruption. Here's Pinatubo, erupted right about here, and we saw a dip in the temperature of the Earth cooled for a few years. And then it rebounded, it warmed up. So there's one example, and you can actually look in these other proxies, see there's other ones like Krakatoa, there's other volcanoes that erupted in Indonesia that actually cooled the Earth, and there's all kind of extra evidence of that in novels and paintings of the corresponding to that one eruption increased the aerosols in the globally in Europe. And so that was like in Indonesia, you could see it from Europe. It's amazing. And you can actually see these internal cycles. So this was a really intense El Nino right here. It's 97, 98. And then we had another one, 2010. And then we had another one here, another El Nino. So they tend to, El Ninos are warm water in the Central Pacific. And that does warm the globe. We get these little spikes. We get the spikes. But there's also this trend. This trend in 1979. Even if you take out the El Niños and some of these dips or some of the La Niñas, so they're cooler water. But even if you take both of them out, you still see this long-term trend. And this is this is a satellite-based observation of temperature. This is not Earth thermometers. This is looking at the air from satellites. So okay, I labored. That's a little long, but I think we got the geologic suspect is sort of I don't think there's that much of a impact. It does impact. It does. We do get CO2 to warm a bit, but most of the impacts are cooling. The impacts of most of the volcanic eruptions are to cool. There are some warming, but we as humans emit a lot more than the volcanic eruptions do. So the last one we have is, well, let's go out in the streets and see if we can find another suspect. So there's another one. This kind of guy has shifty eyes over there. He's sitting over there in the corner. And what about atmospheric composition? So the composition of the molecules in the atmosphere. Let's look at those guys. So we like to look at that. We know a lot about it, going all the way back. Papers back written in the 1800s, early 1900s have been looking at this. So it's not new. The greenhouse effect. We looked at, so basically the visible light goes into is transparent to the atoms, molecules, warms the surface of the Earth, radiates that as heat. It's also light, and some of the molecules in the atmosphere actually absorb those heat, light, those photons. And those, we call those greenhouse gases, because they absorb those heat, and whereas some of the other molecules that goes right through, goes right back out. But there are some molecules out there that absorb just the heat radiation in the Earth, and that's what keeps us nice and warm. If we didn't have our greenhouse effect, it would be like the moon, and we don't want a vacation on the moon because it's really cold and gets really hot there. There's very little atmosphere there. And so that is what we call the greenhouse effect. It keeps us nice and cozy here in the Earth. And so the natural greenhouse effect maintains the Earth's surface temperature about 60 degrees warmer than if we didn't have the atmosphere there. We call that a black body. That's a kind of the physics version. It's just a thing in space that absorbs light at a certain rate and radiates out light. So it would be 60 degrees cooler if we didn't have our oxygen and our ozone and all those different gases that we have, and CO2. So the thing is, okay, so how does the greenhouse effect, we kind of explained that. So are we tweaking those, are we tweaking those molecules, the concentration of those molecules that regulate our temperature and keep it at a nice 60 degree warmness compared to if we didn't have it? And the answer is yes. And here's the last 2,000 years of the important greenhouse gases. The red one is the CO2. The black one is the nitrous oxide, N2O. And then this blue dashed line is the methane, CH4. And if we look back at proxy records of, like, for instance, look at ice cores. When ice freezes, it traps little bubbles of air. And it sort of grabs them as the air freezes, it grabs some of the atmospheric gases in them and traps them. And you build layers, and if you want to know what the concentrations of the gases were at a certain time, you look back in your column of ice, and you basically melt it, and you capture that gas before it gets into the air. You capture it inside of an instrument, and you measure the parts per billion or parts per million concentrations of those gases. And I have friends who actually do this, and they really love it because they get to go out and march out into the Greenland ice sheets and spend the night over there and look at all the stars and drill holes in the ice and can take back home. And so anyway, they put a lot of effort into this to do a really good job to come up with concentrations that they can use to put into models. That we know what the starting times are for these. So if we go back and say 2,000 years, we know with pretty good confidence the concentrations, and we do it at different places in southern hemisphere, northern hemisphere, and then we build up a time series, and that's what this is. So prior to the Industrial Revolution, we were pretty flat, 15, 16, 1700s, 1800s, 1900s, we started to see things really shape up right around here. Things kind of just went boom, sort of like a step, boom. Things like, what's going on? So what could be, just kind of a summary from here we are we're in the police station. We got all the summary. We got the report back to the lieutenant. And so, okay, what do we find out? Natural cycles, nope. Those are likely cooling. They're not warming. The sun is likely, most of it is actually cooling right now. The orbital cycles, we remember we're heading into a little cooling cycle, and we disrupted it, so he doesn't really warming us up. Geology does kind of both, but it's more likely cooling than anything, because it's mostly ash that we're seeing impacting climate. The fifth one that we grabbed off of the street is the one that does the most damage, the atmospheric composition. So just as a reminder, all of those are in business right now. These guys have some part in it, but they're not the main culprit. They all have some suspiciousness. They're all in business right now, but most of them are trying to drive our temperatures down. But atmospheric composition is driving up on much more than anything else. So just as a review of this, driving it is our mechanistic thing that's driving this is the greenhouse effect. It's not. We're not using correlations or anything like that. It's actually a effect of the amount of radiation coming in is absorbed, and we get an increased amount of absorption as we increase the concentration of these greenhouse gases, and we can do this sort of pretty simple physics. You can do some demonstrations of this by changing the overall absorption of the greenhouse effect. How much does it warm? What is he basically using? If anybody's taking physics, you do the Stefan Boltzmann law, and they use that as one of your bases as for making some calculations of the temperature. And so what we've been doing is we've been slowly changing the knob of the concentrations. Think of it as, we're tweaking the amount of greenhouse gas concentration a little bit every year. Boom, boom. Waiting for it to turn, boom, boom. We're seeing that, and we're seeing it enhance greenhouse effect. And what it's done is artificially increase the Earth's temperature by at least a degree Fahrenheit. And that's kind of what we're doing now is seeing that is so if you want to disprove that, you're going to have to disprove the greenhouse effect. And good luck. Okay, so I'm going to kind of transition to that to say, okay, so what do we need to do about it? So where are all the greenhouse gases coming from? That's sort of where do we start? It's sort of like if you want to lose weight, what is your input? What kind of food are you eating? What kind of exercise are you getting? Sort of, trying to translate to something that we can grasp. So what is our input? So what is our global greenhouse emissions? And this is for the whole globe. And the most of it is actually from electricity and heat production across the globe on average. And the second is actually agricultural, forestry, and other land use. So it includes like cultivation of crops, livestock, deforestation. That's big. We know this one's fairly simple in terms of we know what those are. We can if we go out and write down the lat longs of all the power plants, all the things that's emitting, we can go to different continents and do those, and we can calculate. We can ask them how many tons of coal are they burning, how many million barrels of oil are they burning, et cetera, et cetera, et cetera. And we can actually come up with those numbers fairly good within an order of magnitude of the amount of greenhouse gases. And then what's that next? After that is industry, then transportation, then other, and then buildings. So those are our things. If we really want to make a dent, we need to start probably on these top two ones. So the energy production, heat production, I'll go into a little bit of detail on those. And then what do we do about agriculture? Well, across the globe. And these are going to take some ingenuity and changes in lifestyle. Things of how do we do things differently? That's a big thing. So what about New Mexico? That was global. What about New Mexico? So this was the last time they did an inventory. We had it back in 2007. I got this from the Environment Department. So the biggest contributor greenhouse gases were from energy production, about 42%. And then the next was fossil fuel industry, and then transportation. So it's similar, but not the exact same as the global. And then going from transportation down, fossil fuel transportation, and then down to residential, commercial, non-fossil fuel industries, and then agriculture, and then industrial processing, and then waste management. So, but we'd like to look at what's the biggest ones. So energy production, what do we do to power this room, etc. And then these are more like extracting stuff out of the ground, the fossil fuel industry. How do we get our resources to burn to make electricity? How much energy does it take to get it out of the ground? So that's kind of one of the big things too. So what about the average American? So this is another thing I got from this really good book. It's actually published by Union of Concerned Scientists. It's actually good because it has really practical stuff. And they come up with, from the stuff that you buy, just think about the stuff that you carried with you to this room. You likely bought it unless you stole it or somebody gave it to you. So your cell phone, your hat, your notebook, maybe your wallets, hats, things like that, stuff you buy. That is likely the second most, but transportation is the biggest one. So I like to look at that one because that's something that we can easily do by what we buy. And this one's a tougher one because we're sort of stuck in this mode of transportation. Everybody lives far, and it's not safe to, who wants to walk to work? And yeah, you can walk to work, and that's good. I'll show you some examples of what we can do. But it's sort of not designed for that, right? I mean, if you lived in a big city, it's a little easier to do that. But if you lived in Doniana, it takes a little while to ride a bike. You can do it, for sure. You can, but it's a little while to do it. We're not designed to make it easier for folks to change their habits. And then if you look at the other things, so like home heating, cooling, other energy use, other things that are going on in your house right now, probably chugging along while you're not home. And then the food that we eat. So there's a lot of things that we can do. And I encourage you there's this book here. And if you see me later, I can tell you where to get this. But it's free, actually. It's in the library. And you can actually download the PDF. If you have an NMSU email, you can download this PDF thing for free. It's pretty cool. So I just want to pick one example of something that we can do. And I do this in my class. So how many, so for instance, let's just go ahead and do the calculations. I did it real nice, simple for you. So we have a 12,000 mile round, trip that we do in our car. It's pretty average for the U.S. And we get a fairly junky car that gets really bad gas mileage, about 20 miles per gallon, which is not very good these days. So if you do the calculations for the normal internal combustion engine, that emits about 7.5 tons of CO2 annually. And so what? So that's, I don't know how much is 7.5 tons. It seems big, but I don't know how big. So how heavy is that? So everybody knows what a Toyota Camry is, right? Most people do. And that's 7.5 tons is about a little more than four. There's more than four of those Camrys in terms of weight. So imagine 4 Camrys piled up here, 4.7 piled to the ceiling, and that's how much the weight of that is the amount of CO2 is emitted from one car, 20 miles per gallon. And you can adjust that if you have a car that's 30, or if you have a Prius that's 50. But you're still emitting CO2, no matter what, if you have an internal combustion engine. But you're emitting at a much less rate. So you can do the math. You can scale this. It's linear. So that's something we can do. And in one of my classes, what I like to do is, so what if we, on one day of the week, we commute together? One week, one day, one of the 5 days we commute in. How much CO2 would we save over the whole Las Cruces? And they say, well, if everybody does it in New Mexico, all the students in New Mexico, and we calculate how many students are on UNM, NMSU, et cetera. And so how many tons of CO2, and then how many equivalent times of power plant does that equal? We could do that calculation. And it's actually amazing how much you save by just commuting together one day of the week, by finding somebody who goes to NMSU about the same time. You can save a lot. And so that's the kind of games we play to find out what our impacts how can I as an individual make a difference in a globe of, we're over what 7 billion now, somewhere around there, people on the earth. Remember, we are the top producers in terms of our incomes we make a lot of decisions that we burn a lot more CO2 than most people do on the Earth. So I like that. And I want to just kind of talk about some practicalities about our future. Where does it look like going? We did a project with the city of Las Cruces, and we did some modeling for them. Actually, I didn't do the modeling. Catherine Hayhoe did, and she looked at, so what does the future look like for Las Cruces? It was very interesting. And we were looking at heat events, because that's one of the things we're really keen about is, so should we be worrying about our people in Las Cruces who don't have the right cooling systems? We have a lot of people now who's, in the summer, their houses are in the 90s, in the middle of the night, where most of us have a nice little thermostat. We can cool down to at least 80s, right? Or some people like to go down to the 70s, but a lot of people, they can't go down. They don't have the air conditioning. So these are the more people are going to be impacted by climate change when we move that distribution of temperatures to warmer temperatures. That means that the extremes also increase in frequency. You think of it as a distribution. Think of your statistics background. It goes into a statistics problem. Move the distribution to a higher number. Your tails are going to be into higher numbers, right? Right? So basically what we came up with is we did that kind of calculation, and we came more days when we have temperatures above 95, 100, 105, and nights above 100, nights above 80. And currently it's basically we don't have those days. If you go into a place like Tucson, Phoenix, yeah, big deal. We get 80s and they're low all the time, but not in Las Cruces. And there's also a greater risk for prolonged multi-heat events. That's one of the things. And I'll show you a graph here. It's kind of scary. So this is our days, the number of days with highs more than 105. And we had a few days last year. Our highest on campus, we have a weather station on campus that goes back to 1892. And most reliable at 1895, but still pretty long record. Long record. And we use that data to tune this in order to do this. And, we've had a few. Our highest ever was 1994, where we had 110 degrees Fahrenheit on campus. That's our absolute highest that we measured on campus. And we're seeing the number of days increasing. So you can see here's the black line is our observations. So we had a few days where we did have 105, but we're starting to, our trend is going to go up. And depending on the different scenarios, we call them scenarios, not forecasts, because we don't really know, we can't forecast, but we can play scenarios. If this happens, this is how the atmosphere might respond, and most likely. We're actually heading toward this darker line here. And this was the higher scenario. So we're seeing, basically, and I saw a calculation. If you compare the number of days, we're basically heading toward. Toward the end of the century, we're heading toward what Phoenix. That's what Phoenix is, right around here. The number of days. Somewhere like Chandler. I think that was the calculation. So we'll be like Chandler by the end of the century. That's kind of if this is right. So another thing that really worries me is our water. It's like, well, what does climate change have to do with water? Big, huge amounts. And there's like my colleague Dave Gutzler up in the UNM. He's been doing this for like 30 years, and he's a really good resource, and we've been chatting about, so what are the impacts of climate change on our water system? And, and he can get some really sobering predictions on that, and he did. When we had our water meeting in El Paso at the Water H2O Center, they laid it out for us. We got to start working on this. And here's an example. I just picked some climate, some downscale temperatures for northern New Mexico. So this is there, basically Albuquerque and above to the Colorado border and into the Rio Grande basin in Colorado, making a box. So what are the maximum temperatures for the winter? So right now we're dancing around the average winter temperature is about 40.1. And that's a big area. So there's a lot of the areas that get much colder, but then you're also dealing with some of the valleys. So we're above freezing. But if we look in the future. Here's the current, and then we look into out to 2039. The temperature goes up by about 3 degrees, and it goes up to 69. And at the end of the century, we're more than 9 degrees warmer. Average temperature is at 9 degrees warmer in the mountains. So that's, and this is the worst case scenario, the RCP 8.5. That's sort of the high emissions scenario for us, and that has some major implications in our water supply. And this is kind of what I summarized the several reports. There was a Bureau of Reclamation report, Department of DOI, EPA, Department of Interior's DOI, Environmental Protection Agency reports on the Rio Grande. Basically, they all said the same thing. All three separate research groups: less snow, more rain during winter. It's going to impact lower elevation basins like the Rio Chama. More frequent low flow periods. We're already seeing that right now. I mean, things melted out more than a month early. We're down to about 30% or so, 40% of our snowpack this year. Our plants are going to need more water. Plant consumption increase because it's warmer. And remember the things are going to get, their freezing level is going to be higher, so you've got more plant consumption. Increased surface water evaporation. We've got big reservoirs out there that we lose water from. Elephant Butte, estimated to increase by up to 10% more evaporation. And our irrigation water demand has increased by 19% by almost the end of the century. So that's a lot of water. Think about it. Or just the irrigation, the area that we have control over. And another thing I mentioned this earlier is, so how do we mix dust and climate together? A big time. There's actually a picture of the Colorado mountains, the San Juan Mountains, and this is one picture I took off the web by the Snow Optics Lab, JPL. You get this dust on snow, and that's a big deal. And there's a lot of research now. There's actually a whole research group in Silverton that's all they do in the wintertime is they go out there on top of the mountain at 14,000 feet, and they drill down and they take snow cores. And they measure the soil in the snow, and they report back. And they've been doing this for probably more than a decade now. Is looking at, and they've been putting it into models, and so how much because white snow keeps colder, but if you start to pepper, making it darker, it actually will melt faster. And this is basic physics. Albedo changes; things darker absorb more solar energy. So as you put like this picture here, the brown snow, that's going to melt out quicker over time. And you get these dust storms, and it basically peppers all the mountains in the San Juan Mountains. And some of it actually goes up to the Route National Forest, which is up on the the Colorado-Wyoming border. Because I have colleagues up there who have an observation area on one of the ski areas, and they get regularly brown snow up there. So our dust doesn't just stay here. It's not like Vegas, whatever happens stays here. It goes and blows downwind, and we impact ourselves. And it's a feedback mechanism. We're changing our snowpack by aridity. Aridity makes it worse. So that's changing our snow mountain. There's a modeling that's been done. Really good groups have been doing several models, and we've been chipping away several weeks of our snowpack just on the dust. We're melting it out earlier by more than a week. So what about I like to, since I work in an ag college, I like to say, what are the impacts to our environment, our farming, agriculture, our bread and butter, our ranching? So things like the evapotranspiration. Remember, there's evaporation. There's this air that goes from the liquid to the gas phase. There's also things, we're sort of evaporating right now from our skin. We're made of water mostly, and if we're made out of plants, we actually liberate water over time, and so we call that transpiration. So we have the evapotranspiration. We add both the water vapor leaving. So how much water are we losing basically on our grounds in New Mexico? And I just picking on New Mexico, and this is what it is right now on a summertime, the June, July, August. How much water is evaporating from our lands, and it's colored by 10 to 30 inches. So that's how much water we need to irrigate in order to make up for the loss. So the red is about 30. So this is right around, say, 20, 28, 30 inches that we need to irrigate in order to make it even, so balance the water. Less in the mountains, of course, because it's cooler. So we're down to, say, 15 inches. But what about how much will climate change add to that? Remember, it's warming. So the graph on the right is going out to 2039, and this is how much additional evapotranspiration is created by our warming. So the scale in here goes from 0.5 to 1.5. So the red is about 1.5. So according to this downscaling of my friends at University of Idaho, John Abatsoglu came up with this method. Our hardest hit areas are in the northeast. Just like right now, they're getting hit really hard, and that's kind of our Dust Bowl region, the Panhandle, Oklahoma, and they're going to get hit with another inch of evapotranspiration. That's a lot. We can actually make a calculation of how many acre feet of water that will be for irrigating, or how many, et cetera, for much water will be needed for range management. So what about later in the century? So here's our same map, the reference. Here's by the end of the century. And the scale's now changed. It goes from 0 to 5. So this is additional evapotranspiration is added on top of what we already have. So remember we have right around 20 some in the southeast, and we have to add another 4 or 5 inches. So that's going to translate into more water that's needed for our farming. How much water that's needed for our for our cattle, for forage. So it corresponds to a need which it's going down. It's in the Oglala Basin here, and I meet with the farmers and ranchers all the time, and everybody has been saying it's going deeper and deeper to get well water now. So there's less water available, and we need more water. So it's something that's can't be. We can't go in the same direction that we are now. That we can't just do the same thing over and over. I guess that's what do you call that? Expect the same result of doing things over, insanity or something like that. So we got to change our ways. We got to do things differently. So that's kind of the where we are with agriculture is. So how do we do this over? How do we adapt to this? What kind of crops do we need to rethink about how we do crops in different areas of our state? We've got a little bit of time, but things are happening pretty soon. We're seeing this, for instance, right now we've been seeing it drying out, and there's been several papers actually written on the Colorado River, and we had some really good years, but overall general drying for the Colorado River, and we store it. We have these big reservoirs, but like this year, we're likely going to empty out Elephant Butte. We're going to go down to 5%. That was an operating thing. It was last week. There was a meeting in Albuquerque, Bureau of Rec, talked about that, and so it's something we're going to have to deal with very quickly, because this is kind of the thing that's we're seeing droughts. This is the droughts from the last 18 years. We've seen them come and go, so we can learn from what did we do here to adapt and manage ourselves here? Because we're going to have to deal with things like that in the future when droughts are in this exceptional drought. So what are some of the strategies that we had to deal with? A lot in this area, a lot of when this happened, when the drought was this intense back in 2011, 12, that's when this year is. A lot of the ranchers had to sell their herds. They sold a lot of herds, which changed the genetics of their the breeding. It took a long time to get the breeding herds up. So there's some of the things we have to do, and they didn't have enough feed for some of the feedlots. They ran out, and so some of the things they have to is have more on site in order for them to keep operations going when there's lack. And right now, I was up in Clayton last week, and we were talking to ranchers. They're already finding shortages of forage right now of alfalfa, quality alfalfa from the San Luis Valley. I said, well, sorry, we don't have any. You have to find it somewhere else. It's okay, we're going to pay a lot more to ship it from somewhere else that actually has a lot of precip, which there are, but who's going to want to pay for a semi to bring down, because it costs a lot of money for transportation. So this, I just wanted to show you, this is where we are in drought right now, and this is we're going to probably see a lot of this in the next before the monsoon comes up. So what can we do? I'm going to start getting close to closing up for this. So we need to prepare for a changing climate. We need to adapt. So some of the things we can learn from the past, and we can go even further back and say, what did our ancestors do in some cases? when things happen, and how do we use our technology to adapt to things, because we need to, and how do we take care of our people, our families, because we got to put in the social part in all this. We got to think about our neighbors, people who don't have power. Are they okay? You can turn the thermostat down and be all happy and watch Netflix or something. And what about the neighbor over here who doesn't have air conditioning? What are they doing? Do they even have a fan? How are they doing? And there has been some polls done in Las Cruces. People don't even know their neighbors. They don't trust their neighbors to even ask. So we need to be able to break those barriers to be more social, to help out our fellow neighbors. So that's another thing. That's part of adaptation is changing our ways of thinking. And we need to mitigate. We can't just adapt to it. That's sort of like, I got a cut on my arm. It's festering up. I'm getting gangrene. I'm just going to hide it and put some more Band-Aids on it. I need to cut it off if it's got gangrene, right? Because it's going to take over your body. So we got to actually do some major things with mitigation. And things like changing our carbon emissions, investing in clean energy economy, rethink transportation, ... there's a lot of things. I'm sure we're going to get some speakers in here who we'll ask them to include some of those things in. So what are things that we can do? So mitigating things. And then learn and act. So for instance, what are some things as an individual? What is your carbon footprint? There's even a nitrogen footprint out there, but start with a carbon. So what are we doing? Just like that one pie I showed, things we buy. It's a big chunk of the energy we're expending. Because think about it, my phone, we take it all apart, and so where all the pieces come from. It's precious metals, you got plastic, and how many countries did this little thing come from? And we just throw them away, we've got another one. So think through all those things. And so we need to think of other sources of energy, like I mentioned earlier. And then I'll go into bicycling. It's sort of like, some of the things can be fun. That's why I put this up here. It's sort of like, there's some things we can actually have fun doing. And it's not all like, oh, I have to do that? You kidding me? But it's like, let's try to think of things that are actually enjoyable, that we can while actually changing our ways. Just like this kid, it's like riding down the street. It's like, and so let's try to have fun doing it. And we like ingenuity and creativity. Those are the kind of things that really get us going. And we need to get our newer generation to think about those things. How can we do the same without generating this much energy production? That's a task. And sort of, wow, we can do this. So anyway, I'll leave you with that. I always try to end with something positive, something fun that we can do. But there's a lot of things that we have to do, and it's sort of impressive on me because I sort of know what all the pieces that need to be done right now, and it's sort of heavy on me. So anyway, we'll be talking more about this in upcoming speakers. Here's a picture of Greg, my colleague from U of A. He's coming up 25th. He's going to be looking. He'll give you a little more detail than I did on the Southwest, the hotter and more arid, because he was one of the primary authors of they do this national climate assessment, and they do it by region. So he was the Southwest guy. He was the point guy for the Southwest. So he compiled all the information from all the different researchers, and basically he's bugging you for the data. Can you write a section on transportation? Can you write it on cattle ranching? Can you write it on, etc.? He's the guy, and they put this together, and it's a cycle. They have to keep doing this every few years, is to update this report, because things change over time. Climate science is not the same as you learned 5-10 years ago. It's updated. We've got new things, and new things have developed, and more mitigating, more adaptation things that we need to put in, because we need to progress. We need a slope of positive knowledge. And so, Greg's been doing a lot of this. So he's been put a lot of effort into that. He'll bring a lot of really good insights on the Southwest. And he gives talks all over the country on the climate, assessing climate. That's his big thing. And he's actually been he's also, one other project he's involved in is extreme heat project with the city of El Paso, city of Juarez, and Las Cruces. And we've been working with with Greg and the group to look at, so what are some of the strategies for adaptation? So what, we know that graph I showed, a number of days of 105 or more is going to be increasing, so what do we do? Practically, what do we need to do? Really, really, we need to do something. So that's kind of what Greg and his students have been really trying to figure out. It's like we don't have a lot of budgets, so we got to think of things that will work, but without a lot of money. So that's kind of one. You should ask him about that. I'm sure he'll have some really good stories on that. So how far did I go over? There's a picture of the Elephant Butte at the bottom of the lake. So if you go there to time it just right this summer, you can walk on the bottom of the lake before it fills up again.
Mention Earth Day.
Yes, Earth Day, Saturday, 9 a.m. at the Las Cruces Plaza. Be there, have fun. What else is there? There's learn about science. There'll be a lot of people out there, and have fun. Learn. Go to all different booths. And this Saturday.
Does anybody have any questions that you'd like to ask Dave? Yes, Joni.
One of the things I've asked several people, I'm Joni Newcomer, I'm the sustainability manager on campus. When Magdalena ran out of water, all I can think about is we're a lot further down the line than they are. Has anyone thought about if that could happen to us?
Well, as far as I know, we've done assessments, and we're still doing. We meaning the community, the water community. And I don't really have that much of a stake in that, but we've been looking at the water assessment. How much water do we have in New Mexico? Some of the basins we have a fairly good knowledge of how much water. So how many years of water? In some areas we have like 50 to 80 years of good water in this particular basin, but some areas we don't. And I know I've talked to people like, for instance, the East Mountains of Albuquerque, and they've already run out, just like the Magdalena. If you go up to on the east side of the Sandias toward Santa Fe, they've already run out of water, and they've had to bring water in, and they've like. My parents have a place up by Chillicothe on the south side, south of 40, and a lot of their neighbors they're out of water. Basically, they had to go to tanks because they didn't have enough money to drill more wells because it takes a lot of money. You got to have money to have water, and so I think that's going to be a big issue. And I think it's going to be addressed. It's happening in the rural areas already, so. I think, and even we've talked to some folks, ranchers in Panhandle, Texas, and actually one guy, he said that water is more valuable than the oil and gas that he had in. So he actually transitioned his gas lines to water because he ran out of water at his house. So he said, I'm going to use my gas line. Water's more important than gas right now. So I think we're going to see more of that kind of thing going on. And that was like over in Muleshoe over there.
Another question? And what about Cape Town? Isn't Cape Town, South Africa, going to be running out of water?
Hello, I'm Mary Lee Souls. So this whole discussion has been pretty much climate change is real, it's scientific, it's demonstrated, and people are causing it.
Yes.
And yet, there's something out there that people don't believe that. So are you experiencing anything in this community that is that denial dynamic? And
All the time.
and what do you do?
Wherever I go, there's always somebody who's going to say, nope, that's not how it works. And so, well, okay, tell me how it works. And, a lot of times in some of those, giving you more data doesn't work. They won't listen to more data. It's a worldview that change. It's a lot of it's tied to how is it going to affect me if these are true. If you think those are true, what are those going to affect my? Is it going to cost more for my electricity? Is it going to cost more for dot dot dot? And how do we even know these are true? Because we don't. I mean, there's a lot of things we in science, there's always uncertainty, right? We don't know things to 7 decimal places accuracy, but we don't need to know that much accuracy. Just like if you were in the military, if you knew the accuracy that much, you would be dead because you would be shot. So when you shoot somebody, you protect because you have a hunch. You have a pretty good sense of, okay, these guys are coming at me, and I need to defend myself. And the same way with the insurance industry, same way. It's risk management. If I know the risk, the pile of risk, which one is the highest risk? I want to sort of protect myself from those. And I sort of kind of mold it that way, and sometimes it doesn't work, sometimes it does. But it's like a lot of times if science doesn't help. I can print out, I got like 1,000 papers on climate science. I can print them all out and I can go through one at a time. That's not, and it still wouldn't help. It's more of, okay, we don't know for sure. Or, what about this? And I go through with some of my climate other groups that we have, and we go through the questions that we get, and we talk about them. Because it's like, how do we respond to this question? Oh, here's how we deal with that. And there's actually whole classes you could take. I forget the name of the class now. Is it Australia, Queen's College or something in Australia? But anyway, on how to deal with those who don't trust the scientific explanations. So.
What about taking Ronald Reagan's view? Remember the whole ozone issue? And when he was presented with the idea that the hole in the ozone was going to cause serious problems for the Earth, he basically said, well, if you're right, if you're a scientist and you're right, we're going to have a really serious issue on our hands.
Right.
And if you're wrong, and yet we make a change, well, it's no big deal, right? We make a change, and it has no effect. So if we make a change now, and we're wrong, well, then there isn't going to be any big deal, right? Do you understand my argument? He was saying that we need to cut the fluorocarbons out of the atmosphere, and if we're right, we've done something great, and if we're wrong, it's no big deal.
Right.
So wouldn't that be the same if
there's a
we
really good cartoon that,
take
that I
efforts?
share. I think we have it posted somewhere about So even if we do things, if it's not true, even if we do all these things, we make a better environment, a better way of life, and it's sort of.
But if we switch to clean energy, is it going to be that big of a deal?
Yeah,
for us?
I know, but the thing
it's sort of an insurance
the questions
policy.
I get are say, well, we can pay for it, but the people who are in other countries who are very poor, they can't pay for that, so they're going to still suffer. We can pay for it, so we're pushing our economy on them. That's the kind of questions I get. I'm not, that's what I have to deal with and respond back. It's sort of like I can buy solar panels for my house, and mitigate. But somebody in India who makes 1/100th of what I make can't do that, and we're asking them to do that. So those are the questions I get, and we're imposing things on other people.
Right.
So that's the.
The fluorocarbons actually provide an interesting point here. And that is sometimes people seem defeated because of the scale of the problem. It's like no legislation we could enact will make a significant change. But if you look at the fluorocarbons, they were on an upward trajectory just like CO2 was. And then at the time of Reagan, they were banned or greatly diminished. And the pattern has stopped and is now reversing.
Yeah.
And so, there can be effects.
Yeah, and there was, that was the Nobel Prize actually was for one, I forget which year now, for the effect, the actual mechanism. And I actually attended one of the lectures. It was at UC Davis, and the guy who was actually, it was a team who got the Nobel Prize for the ozone hole. And, they laid it out. It was like a 2-hour lecture, and they went to the chemistry of the thing. And it was like, and they had published it already, and it's sort of like, that's, do you doubt that? Do you doubt somebody's Nobel Prize, in peer-reviewed literature of this mechanism? That's something that, okay, you could still doubt it, but what basis do you have? Do you have peer-reviewed literature to say that it's not correct? And if it is, you should probably publish it. because then you could probably get a Nobel Prize too for disproving somebody else's Nobel Prize. Yeah, I encourage people to do that. If you can actually say that the greenhouse effect is wrong, I would go for it. See if you could come up with an experiment that says it's not correct, or that there's something else going on. That's how we work in science. Is to say we try to disprove everybody else. We try to up somebody else's paper, and that's the way science. But it's through the peer review process. It's got to go through the rigors of testing and scientific process.
Another question?
I'm Yining. Thank you for your sharing. My concern is hydrology. This is my research concern, and I'm really interested in climate change. Based on my previous research, I got some result from climate change in one small local valley, irrigation valley. If I used the long-term climate projection, I got a positive result. Actually, with those climate change in that small valley, my result showing we will get higher stream flow. Just look at those results, I think it's positive. It's showing farmers, local people get more water from river. As a climate scientist, what's your idea or what's your suggestion when we do research in different scale? Because in your research, in your speech, you made conclusion to research in terms of large scale, like the whole planet and the whole land. But when we do local scale, lower scale research, what the difference or what's the climate pattern shift effect on local nature system?
Yeah. Thanks for the question. And basically, climate impacts are local. So when we do something, we like, when we run models now. I mean, in the past we did big scale things because we didn't have the processing power. But now we can run down to 2 kilometers and find out what's going on in the subbasins. We call them like HUC, hydrologic units, into like 4-digit HUCs now, which are very small. Like the Rio Grande Basin's a 2-digit, which is pretty big. Most of New Mexico, and we can go down to smaller. And then we have to have the driving data to actually know what's going on. So what are the climate driving information to drive your hydrologic model? So ultimately, I know folks at Wary here on campus have been doing that for small parts of the Rio Grande system. And there's other places. I taught this summer in Colombia, and they were doing the same thing in some of the smaller, because they use in Colombia they use their rivers for making electricity, where we don't have that here. We don't have hydroelectric, whereas they want to really know, because they want to know how many cubic feet per second are coming down, 50 years from now, down in that one location, which is very localized. And I'm sure there's other places like the Columbia River probably needs to be downscaled to a very small area. So that's we can learn things from both the large scale and then the small scale as well. And there are some areas that are actually getting increased amount of flow, but it's compressed. Like especially in the Southwest, which I'm most familiar with, we get a much more higher flows, but it's at a shorter time period. It's coming down very quickly because of the snowmelt time is faster and warmer. So we get peak flow higher, but overall a month and a half earlier than the past. So those are really useful things. So how do we manage our water collection when we have those? When we have the changes in timing of stream flows and the flow amounts are different. So yeah, those are really good question. Yeah.
Another question?
I just heard an author speaking on C-SPAN, Jeff Goodell, and he's written a book called The Water Will Come. and his focus is on coastal communities and the rising sea level. And so the impression I get is we're at a point where sort of no matter what happens, science is going to be vindicated in a sense, because we're going to end up living through some or most or all of this before, if we are able to come together to a correction. So his focus is on how vast chunks of major areas are going to have to relocate, or even the Navy is planning on their major shipyards. They figure their shipyard out there has a life of another 25 to 50 years. So is that a correct assumption, that it seems like we're going to live through some of this, which is going to probably vindicate the science, and then it's just puts us further into the mess?
A lot of it time's going to tell how well we're doing with this, but it's sort of this, some of the predictions that were done in the 80s are, we were actually pretty close to what we were predicting what they're going to be in 2010s. So we didn't have the accuracy, but we were in the right trends. There's a pretty good chance. I mean, in 30 years, we'll be seeing some of these things like we showed on that report from the Bureau of Reclamation. But keep in mind, we still have. We got wet periods, dry periods that are still going to be going on during a slow climate change signal. Just like there's a paper I read the other day was looking at the sea surface temperatures over the last 100 years. And basically, you've got these big oscillations in there. But if you take apart the signal, you've got this really long-term trend of warming, and it's sort of that. We're slowly seeing these changes in sea level rise, and they're impacting. I had a meeting a few years ago with folks back east, and they're already planning on, how do we deal with these hurricanes, that have come in, and the sea level rise slowly inching up, and with the water levels getting higher. So how do we deal with protecting our cities, like New York and Miami and all those big cities? And so dealing with like structures. It takes a long time to get things permitted, decades. I'm dealing with BLM, just getting a project, takes more than a year. Think about if you wanted to put a seawall in the middle of the ocean, or something to change the wave pattern, the wavelengths. How many years is that going to take, and how many $1 billion is that going to cost? But those are the things we need to think about. And how do we fund those things and convince engineers to build those? Yeah, good question.
Well, how about one more question, and then we'll let you all go.
I could probably yell out. Just interested in feedback loops. Appreciate your talk. Any comments on methane hydrates melting in the ocean on the continental shelves and potential impacts to climate from that?
Yeah, there's a lot of places where we're looking for methane, and I don't know too much about that. The oceanic sources. I know there are some in. I would have to look into more about that to give you a good answer. The one I know more about is in the Arctic. I've got some friends who do some work in the permafrost, and there's methane trapped in the soils. And as the permafrost melts, it's releasing large amounts of methane from the Arctic. And it's amazing how much. And a friend who's actually up there, it was a few years ago now, probably 5-6 years ago, he was taking measurements, the concentrations and the depth of the permafrost. It was getting shallower. It was, there's a modulation, freeze, melt, but it was slowly getting thinner over time, and it was getting close to that layer where there was a lot of methane. And there was a few places where he actually could light the soil, and it would burn. This was in the Siberian continent. Asian, well, up north, but it's sort of, that is a lot of concern to me, and I don't know much about the oceanic sources of methane. I'm sure there's a lot of things work on that area, and that's another area. There's so much to know to investigate. So thanks for your question.
So let's all thank Dave for an uplifting talk for our future. And please join us next week for Greg Garfin's talk. And please look at the flyers and NMSU hotline and et cetera. And we'll probably also get some information out on NPR so that you'll be able to look at the NPR website and find out when the next talk is. Thank you all for coming.